So my name is Professor Buckley. I'm a professor here in the Department of Physics and Astronomy. I am a particle astrophysicist, or a theoretical particle astrophysicist, if you want to keep adding words to it. My background actually is in particle physics. I started as a theoretical physicist thinking about creating new particles at the Large Hadron Collider. And for reasons I hope I will explain tonight, I ended up thinking about the largest structures in the universe and the earliest times in the universe and what we can learn from them about new particles that I was hoping to find at the Large Hadron Collider. So tonight, what I'm going to do is try to tell you about this mysterious thing called dark matter that exists in the universe, probably exists in this room right now, passing right through you. And what really I want you to get out of this is how we know that this stuff exists. And then from there, I'll tell you what it might be, I'll tell you how we're looking for it, and tell you how we might be looking for it in the future, where I think sort of interesting directions might be going in the next couple of years. The real interesting thing is, what is most of the universe? And so you can just ask a very simple question, what is the universe made of? Simple question. And you go out, and how you answer that question, you go out and you look. So here's the Hubble Ultra Deep Field. Everything you see in this picture, except maybe that with the sort of a lens flare on it, is a galaxy. So this is just Hubble looking at one point in the sky for a really long time. And so you just see, oh wow, there are a lot of galaxies. They're glowing in photons, and if you look at the spectrum of those photons, you start seeing that it's filled with chemical or elements similar to the ones that we have here, right? So it's filled with stuff. That's what we're looking at. Things that are like the stuff that we're made out of, stars, the same stuff that planets are made out of, trees, us, New York, so on, right? It's made of protons, neutrons, and electrons. And we observe them, as I said, by photons. And so this is what we see, like literally see, if you take a telescope and point it anywhere. And so what we're seeing are things made of what I, as a particle physicist, would call the standard model particles, right? This is just the stuff that we know exists that we've created in a lab here on Earth. So here's a little picture of the standard model. If you haven't seen Particle Fever, I highly recommend it. It's a very good documentary on actually discovering new particles at the LHC. But basically, we know the universe is made out of quarks, which come together and form protons and neutrons, leptons, of which an electron is the lightest charged one. And then there are the uncharged electrons called neutrinos, which are a lot harder to see, but we can still find them. And then what we think of as forces, like electromagnetism, are mediated by what are called gauge bosons. And those are the photon, the gluon, and two sort of strange ones called the W and the Z. And then there's gravity, but we can't fit gravity into this picture, so we don't put it there, but we know it exists. And then there's sort of the linchpin of the whole thing, something called the Higgs boson, and this is not a talk on the Higgs boson, so I will skip past that right there. However, everything we see is really only 4.6% of the energy density of the universe. So everything that you see, if you look around here, or if you take a telescope, point it at any point in the sky for as long as you like, you're only seeing a small fraction of the energy of the universe. In fact, it's a little bit worse than that. Only 10% of that, let's call it 5%, so 0.5% of that total stuff in the universe is actually in a galaxy. So when I showed you that picture from Hubble, and it's showing you nice, beautiful, glowing galaxies, that's 0.5% of everything in the universe. So the terminology that astronomers use, it's really sort of mangled terminology from particle physicists, is regular matter is called baryons. Baryons are not electrons, but because an electron is very light, if you know where the protons and neutrons are, you know where the electrons are. So they just call that baryons. And then, that's 5%, and then, 10% of that is the stuff that you actually see. And the rest of this is something unknown. It's really two unknown things, and we have given them similar names. Dark matter and dark energy, and they, as far as we can tell, have nothing to do with each other. The dark means I don't know what it is. Dark energy is significantly more of the universe than the dark matter. I have absolutely no idea what this is. Really just none. All I know is that it exists. It's the thing that's making the universe, make the universe expansion accelerate. So this was something that was discovered around the turn of the millennium, and that's basically all I'm going to say about dark energy because I have no good ideas about it. But dark matter is sort of this wedge of the energy density. It's about 26% of the total energy budget of the universe. And so if you're doing counting, this is about 70%. And then, 5% is the regular stuff. And this is something mysterious. It is matter. And I'll try to explain what I really mean by matter, but basically I mean something that clumps together. Right? One of the things that matter does is it clumps together to make a planet that I can stand on. I don't know that dark matter comes together to form planets, but it does kind of come together on astrophysical scales. So that's why it's matter as opposed to dark energy, and the dark means that I can't see it. So that's a really extraordinary claim if you think about it. I'm saying that you look out in the universe, you see a bunch of stuff, but there's really 5 times as much stuff that you are not seeing. It's a really extraordinary claim, and so it should require extraordinary evidence. You want to believe that there is this stuff out there, I better be really sure. Right? So for a significant part of this talk, I'm going to try to go through those pieces of evidence, and I really think you can group them together into 4 major pieces of evidence. If you're in my cosmology class now, you can zone out for a little bit. This will be on the test for them. The rest of you can take my cosmology class to learn more about it. Those 4 pieces of evidence, I would say, are rotation curves of galaxies, evidence from something called cosmic microwave background, Big Bang nucleosynthesis, and interestingly, direct images of something that is invisible. And then there's kind of a 5th piece of evidence, which is that when you simulate how the universe should look, it doesn't look right until you include dark matter. And so I'm going to step through each one of these. I just wanted to kind of put everything up here once so that you could get a picture of what's going on. So the first piece of evidence is how we kind of got the first evidence that there was a problem, the solution to which I call dark matter. So you have this picture of a galaxy. It's a beautiful pinwheel. This is a galaxy similar to our own, right? It's a spiral galaxy. If this was the Milky Way, we would be living somewhere over here, which is not out in the complete blue east. It's sort of a nice suburb. But this is a galaxy, and it looks like it's spinning. And it is spinning. Right? If you look at these things, you can see that it is actually the stars and gas that make up this galaxy is actually rotating around. And that means that it must be held together, right? Things don't move in circles unless there is a force pulling it towards the center. And what is that force? It's gravity, right? So for the stars and the gas that is in a galaxy, there is some central force, that's gravity, and gravity pulls proportional to the mass of the thing that it is pulling, but also the mass of the thing that is doing the pulling. So if you can measure the velocity of any star at a given radius from the galactic center, you can determine how much mass is inside a sphere centered on the galactic center. Right? And so you can just go out and do this. And what you do is you take a galaxy and you measure how fast stars are moving around that galaxy at different radii. And this is kind of very schematically what you expect to see. Near the center of a galaxy, the enclosed mass, if you draw a sphere and plop it down right there, there's not that much mass inside the center of that sphere, so stars here should be moving slowly. And then as you move out, you're enclosing more and more mass, and you're enclosing more mass faster than you are moving away from the center, so you have to move faster to stay on your kind of arc to go around the galaxy. So it should increase, and then it should get to some maximum point. And at this point, basically, as you move out, you're not grabbing more mass of the galaxy internal to yourself. And so you're not moving, you don't need to move as quickly to remain on a bound orbit. And so you should slow down out here. Now, in the 1970s, astronomer named Vera Rubin went and measured this. And what she found was that you start slow and you speed up, and then you hit some speed, and you basically stay moving at the same velocity moving around stars. Stars out here are moving around this galaxy at basically the same speed as stars here. What that looks like, so this is from one of her papers, so this is radius from the center of these galaxies, and these are the rotation curves. And you see they kind of plateau, right? They kind of become flat. We show you a slightly different version of that. Same thing, distance from the center of a galaxy, and then you hit this sort of plateau of velocity. And then you can go and you say, well, let me count up everything that is glowing in that galaxy, every star, every scrap of gas, and let me add it all up and figure out how much mass I can account for based on the brightness, right? A star has a certain amount of brightness for a certain mass. And it's a difficult problem. Like a mass to light ratio, which is what you're trying to build there, is a difficult thing. But you can do your best guess on that. What you'd find is what I told you first. You should come out to a maximum velocity, and then you just should kind of trail away. Stars further away should move slower. Otherwise, if they were moving as fast as they were seen to be moving, they are moving so quickly they should just fly off in straight lines. The galaxy would just spin apart. And so either you believe that you are looking at all of these beautiful spiral galaxies at a special moment in time when a bunch of stars that have no business being near each other all got together and said, okay, we're going to look like a pinwheel. Everyone do that, and then in a million years we're going to be flying apart. Right? So either you believe that somebody's out to get us, which I try not to believe when I'm doing science, or you believe that there is just something else that has to be filling up the rotation curve. Right? There's extra mass that is just hanging out in the galaxy that we're not seeing. Right? And so this curve is basically the difference between everything that we can measure, that's the stars, that's the gas, and what we're seeing the rotation curves telling us. So this is evidence that there is something that is just literally dark and matter. Dark doesn't show up as glowing, and matter means it is clumped around the galaxy. And it's very extended. We live about 8 kiloparsecs from the galactic center, so if this was our Milky Way, we would be living here, and so we'd be kind of living on the tail, like where things should be slowing down. And the dark matter just keeps going way, way past the edge of where the disk of a galaxy ends. And you can see, actually, we don't know where it ends in these galaxies. And that was one piece of evidence. There was actually an earlier piece of evidence which basically no one believed, or didn't really take that seriously, and it uses a similar idea. It comes from galaxy clusters. So I was just talking about spiral galaxies, which is sort of the thing that we're embedded in. Spiral galaxies and galaxies of different kinds are actually embedded in even larger structures. They're embedded in clusters of galaxies. And so this is the Coma cluster. These are stars, you can tell by the lens flare. But everything else here is a galaxy that you're looking at. And they're all bound together. There are more galaxies here than there are in other places in space. So we believe that this is a gravitationally bound object in the same way that we believe the Milky Way is a gravitationally bound object. And so you can play the same trick that we just did with the Milky Way. Milky Way, we had this spiral and everything's kind of moving around, and you say, okay, I can measure how fast everything's moving and measure the mass inside. The cluster is kind of a big cloud. Right, but everything is still moving, and you can use some assumptions about how it should be moving to take a velocity and measure a mass. And so this was Fritz Zwicky. He was incredibly brilliant. Apparently, he was difficult to get along with. He came up with some amazing ideas that basically no one took seriously. I'm not really sure why. This is him demonstrating one of his ideas, which is the spherical bastard. That is somebody who looks like a bastard no matter which way you're looking at them. I feel like he ran into had that face on a lot. But he was brilliant, and he was right. He was right about a lot of things, and it just turned out no one believed him until for a very, very long time. So he looked at actually the Coma cluster, the one I just showed you, and he used the motion of the stars to weigh the galaxy, and then used the brightness of the stars to try to figure out how much mass there could be in stars and gas. And what he found was that in order to explain how fast the galaxies were moving, the Coma cluster would need to weigh 160 times more than he could plausibly account for, given all the baryons, the stars and the gas. He was using some very old numbers that we now know to be old and incorrect. It was specifically the Hubble parameter he didn't have right. Modern measurements say that you do need more mass for the Coma cluster, but it's only about 10 times the mass of the stars rather than 160. But still, he was right in his observation. and he just was working with the numbers that were available at the time. And he, in fact, coined the term dark matter. He coined it in German, but he coined the term dark matter because, again, it is just stuff that he couldn't see that was clustered, right? It was in this galaxy cluster, and it just needed to be there. Otherwise, you have to believe that this moment, the cluster that you're seeing was about to fly apart, right? And you're not actually seeing a gravitationally bound object. You're seeing something that's going to fly apart, and you have to believe in a conspiracy, right? You're looking at this one moment in in cosmological history where these galaxies have all gotten together and they're all going to leave again. And that doesn't seem likely, so if you believe that it's actually a gravitationally bound structure, you have to believe there's something you can't see. Now, all of that's saying is not that there is something new that isn't material that I know, like baryons, like the stuff that's made out of this table. If I filled the galaxy with many, many quadrillions of this table, that would be dark matter. I wouldn't be able to see. It would not glow like a star. It wouldn't glow like dust. It's just kind of at an awkward size, and you wouldn't be able to see it with telescopes. So how do I know not only that dark matter exists, but that it is something truly new, right? Something that I can't fit as a particle physicist into my standard model. So what we're going to do is we're going to look further away in space. And because there is a finite speed of light, if I look further away in space, I'm looking backwards in time. The universe is expanding. So as I look back in time, I'm looking to a time when the universe was very, very small. That means that when the universe was very dense, and that means when the universe was very, very hot. Right? So this is sort of a cartoon of the universe. We're looking out here, and as I look back, the universe is evolving, and it's evolving backwards in time to a moment when the universe was so hot that electrons could not remain bound to atomic nuclei. Right? So you have protons and neutrons, they form nuclei, but the electrons, every time they try to fall in to form hydrogen, right, a photon comes along with enough energy to just blast that right out of its orbital. Right? So before that time, the universe was not transparent to light. Right? A photon moving along would see a free electron and scatter off of that. So photons would just keep bouncing through this soup of very, very hot electrons and protons. But the universe is expanding, so eventually it cools. And it finally cools enough that an electron can come down, be bound to a proton, and form neutral hydrogen, and then neutral helium, and all the other light elements that are around. This happens, you can calculate it, about 370,000 years, more or less, after the what we'll call the Big Bang, time equals 0. So that's when light can finally travel any appreciable distance. So before that time, light was just bouncing into things and not going anywhere. And at that last moment, finally everything cools down, and whatever photon was traveling in this direction, instead of bouncing off of an electron, it just keeps going and going and going and going. And it goes for the next 13.8 billion years. And if you point a radio telescope at any point in the sky, you will see that photon. Right, or see a photon coming from what we call the surface of last scattering. And this was actually discovered, this is a cosmic microwave background. It was discovered here in New Jersey by scientists at Bell Labs. And what I'm showing you here is the sort of best picture of the CMB from a space-based telescope called Planck. This, kind of think of this is, you should put this on a globe and then stand in the middle of the globe. Right, so you're just looking at different points in the sky, and these are hot and cold spots on the CMB. And what I've actually done is, or what they've actually done, is they took the average temperature of those CMB photons, which turns out to be about 2.7 Kelvin, so 2.7 degrees above absolute zero, and they subtracted off the average temperature, because the CMB is almost exactly the same everywhere you look. These hot and cold spots are 1 part in 10 to the 5. Right, so it's 1 part in 100,000, slightly higher, slightly colder, right? And you can see there is a pattern in here, right? It's a random pattern, but if you look at it, you start seeing, there are patches that are big, there are patches that are small. There's sort of some information here. There's like an average patch size of hot and cold. And this tells you a tremendous amount about what the universe was like way back at this moment of last scattering. Why are they slightly hotter? photons from there are slightly hotter than photons from here, or slightly colder than photons from here, right? They're slightly hotter or slightly colder because there are some very, very slight deviations in the amount of matter and energy at different points in the universe. And I'm not going to go into why that occurred. We don't really know. The key word is inflation if you want to look it up. We're not going to get into that. We're just going to take it as an initial condition. This happened, we believe. And we can use that to kind of figure out information about what's going on in the universe. And the first thing you want to look at is there's like an average spot size on the CMB map. What is that average spot size? So you build what's called a multipole map of the power spectrum of multipoles of CMB. Who here has had to do quantum and fit to YLM spherical harmonics for hydrogen atom? Anyone have to do that? All right, so spherical harmonics, you have to fit things, they're a way of describing maps on a sphere. And so all we're doing here, you do that, and it's really, what this is saying is sort of how many fluctuations are occurring at a given angular size. So a physicist or astronomer would be using these multipole moments, but physically you can convert it to an angular size on the sky. And you see there's this big peak at around 1 degree. So about 1 degree on the sky is the size of the most common upward or downward fluctuation of the CMB, the ones with the most power. And you see there's kind of this interesting structure. There's a peak, and then there's a second peak, and a third peak, and a fourth, and a fifth, and a sixth, and seventh, and you keep going out, and eventually the kind of exponential decay kills you. But this is, by the way, real data, and you can see the error bars there, and you cannot see the error bars there. Like, Planck is an incredibly sensitive instrument, right? There's no point in building a better version of Planck to do this kind of measurement because they have basically the best possible statistics they could get. There is interesting things to do out here at very, very small angular scales, but to do that you don't actually need to go into space. You build a telescope, you look at one patch in the sky, and most of those actually, or several of those are in Antarctica. So there is still interesting work to do in the CMB, but so for our purposes, we just need this. So where is that peak coming from? So imagine you're in the early universe and ignore the fact that you're about to be blown apart by extremely hot photons, but you're in the early universe and there's these slight patches of overdensities and underdensities. Don't worry about where they came from, they were just there, right? And there's this soup of electrons and protons and photons. And they're actually going to be sound waves of photons moving through the universe, actual sound waves, right? Not electromagnetic radiation, but like density waves of photons. And what they're going to do is they're going to collapse into regions that are slightly overdense, right? Because gravity pulls, right? So the sound waves are going to come in, they're going to crash in, they're going to heat up the matter that happens to be living in that overdensity, and that's going to cause the pressure wave to bounce right back out, right? I'm very proud of this. It took me a long time to do a keynote. So the sound waves are going to come in and go back out, and they're going to do this at all scales. There are going to be big fluctuations where sound waves come in, there are going to be small fluctuations where sound waves are bouncing in and out, right? And there's nothing special about any particular size of these fluctuations until that moment when the CMB finally stops, or where the photons finally stop scattering off the electrons. And at that last moment, if you happen to be a fluctuation where the sound wave has collapsed for the first time, you've made this matter the hottest it will ever be. It's about to bounce back. It's about to cool. So at that instant, things that are exactly big enough so that the sound wave of photons has had time to move in and collapse into the center, by coincidence, at that moment when the CMB finally kind of occurs, that moment is as hot as it's ever going to be. And if you happen to be a fluctuation so that the sound wave has come in and then went right back out and is about to crash back in, it's going to turn around and come back again. At that moment, it's the coldest it's ever going to be. And that is where you're getting your first peak. Your first peak is the things that are crashing in for the first time, the largest structures that have had these things come in. And the second peak are the ones that came in and then went back out. And the point is that the only thing that's heating these photons up are things that care about photons. which means things that interact with photons, which are not dark matter. Dark matter, by definition, I can't see. I can't see means photons don't interact with it. So, by looking at how this exact structure of this peak, and then this peak, and this peak, this one, all the way down, and you fit to this, and it's a complicated fit. But hopefully I've convinced you at least that the size of these various peaks should tell you about how much stuff that cares about photons is living at the bottom of these potential wells in the very, very early universe. So that tells you about the amount of baryons, not a normal matter. And it just turns out, when you do this calculation, you find that the energy density of the universe in baryons is 5%, and the energy density that has to be in dark matter is, call it 25%, 26%, something like that. Right? And you get very, very detailed numbers. Right? You actually can get these things out to about 3 significant figures at this point. Another thing that you can do is look not at light from the early universe, because you can't look earlier in the universe than the CMB. By definition, that's the last moment that light could, or the earliest moment that light that was emitted could reach us without hitting something first. What you do is you look at the gas that's in the universe that you hope has never gone through a star. If gas goes, falls in, forms a star, the star explodes, throws a bunch of gas back out into the universe, it forms heavy elements. And those heavy elements we're very happy about. There are the stuff that we're made out of, right? So it's good that there are supernovae out there in the universe. But if you just look for patches of gas that never got near a star, you can figure out how much of the heavy elements were produced in the very, very early universe, when the universe was even hotter than at the moment that I just told you about where the cosmogenic background comes from. And so this is what we call Big Bang nucleosynthesis. It is the nucleosynthesis, the formation of heavy elements, because the universe started so very hot. And heavy elements here are heavy elements in terms of what an astronomer would consider heavy elements. I guess in astronomy, it's hydrogen and metals. I don't know if helium gets counted separately. So you basically just have hydrogen, and then there's a little bit of helium and deuterium and helium-3 and lithium-7 and basically nothing else. Everything past that was formed in the star later. And again, you have to do a complicated fit, but the point is that the formation of heavy elements matters only about the type of stuff in the universe that cares about what's called the strong nuclear force. The strong nuclear force is the thing that's holding your nuclei together. Dark matter, it turns out, does not interact with the strong nuclear force. And so it does not participate in the formation of heavy elements. So all I'm showing you here is if I vary the amount of baryonic matter in the universe, you have these different amounts of helium-4 and deuterium and helium-3 and lithium-7 that will form in the early universe. And then you go out and you do your best job measuring it. And the measurements are these horizontal lines. And you can see there's a single value for the amount of matter, in the regular matter in the universe that explains almost everything you can see. Notice lithium-7 is a little bit off. It's a long-standing problem in physics, and we're not quite sure what's causing it. But there seems to be just one value of regular matter that works, and that value is much lower than the amount of regular matter plus dark matter. So that's another piece of evidence for the existence of something that was present in the early universe but didn't participate in the formation of heavy elements. So that's another piece of evidence for what I call dark matter. The last thing you can do if you want to find the evidence for dark matter is you just go look for it. Right? Screw around with all this fitting to early universe multipole. No one wants to do that. Just go look. Right? So that's a bit of a problem because it's dark and I can't see it. But here's a picture. This is a picture of dark matter. The dark matter is where it is blue. What I'm looking at here is what's called the bullet cluster. You can see, or maybe if I tell you, there's an overdensity of galaxies right here, and there's an overdensity of galaxies right here. Those are the galaxies in a cluster. So the bullet cluster is 2 clusters of galaxies that relatively recently, I'm not quite sure, probably tens of millions, hundreds of millions of years, relatively recently, hit each other. And so these 2 galaxy clusters hit each other, and they just kind of pass right through. Specifically, the galaxies pass right through. Galaxies on these scales are point particles. We're looking on enormous scales in the universe. And so the odds of a galaxy in one cluster hitting a galaxy in the other are basically zero. So you just threw these point particles at each other, they went right through. The red is the location of the gas that was in the clusters. And it's red because they're looking at it in X-ray, and they just color the X-ray map in red. And this is actually where the bullet cluster gets its name. Gas, when one cloud of gas hits the other, they interact. Right? It's so spread out and they have these electromagnetic interactions, they actually interact and they stop. When you throw one cloud of gas at another, it will stop. Unlike the galaxies, which just move straight through. And they get this little bullet of gas due to ram pressure. So we can tell that these two galaxies hit each other and the gas stopped and the galaxies moved through. This is actually where most of the normal matter in a galaxy is. And then I do something, or not me, other people, do something very, very tricky. We know about dark matter because of its mass. We know that it exists because it interacts gravitationally. So what you do is you look for things behind the bullet cluster. So you look at these background galaxies that are directly behind the bullet cluster, and you look to see if there are light rays that, as they travel from that distant source to us, have been bent by the gravitational pull of all of the mass that exists in the bullet cluster. And this doesn't matter about whether it's dark matter or baryons or gas or galaxies. It just cares about whether there's matter there. It gets bent. And you can do that, and you can build a map of where the matter is in the universe. And so if it was just that we were screwing up how gravity worked on enormous scales, then we would get a map that put all of the matter here, because that's where all the baryons are. There's almost no baryons, as I said, inside the galaxies. It's all this gas. But we don't. We find that the map of where the matter lives is there's a bunch of matter here and a bunch of matter here. So what happened is two giant clouds of dark matter that just happened to have some gas and galaxies in it smash into each other. And the dark matter went right through the two clouds. They're just moving out this way. So this one came in from there, stopped here, this one came in from there, and at this moment is right here. The galaxies, because they didn't hit anything, just kept going, and the gas smashed into each other and stopped dead. And so as Sean Carroll once said, dark matter, most of the universe cannot even be bothered to interact with you. Right, so this is, in my mind, one of just like an incredibly simple and beautiful argument for the existence of dark matter. Not that we have just, it's not saying that we've just screwed up gravity. So the other thing I wanted to show you for pieces of evidence of dark matter is just comparing simulations. So this is not my work, this is Andrew Ponson. What they're doing here is simulating the universe. Time is clicking by. So he just starts the universe very, very early on and just throws in dark matter with these tiny little fluctuations I told you about that matter so much for the CMB. And you build this incredibly beautiful cosmic web, this lattice, because matter, gravity pulls, right? So if you start with a little overdensity, right, then stuff falls into it and becomes a big overdensity. Galaxies like our own are living more or less at the nodes of these cosmic webs, and there are these big streams of dark matter that are heading in towards us with smaller galaxies or smaller structures in them. So if you could see the night sky in dark matter on the largest scales, this is what it would look like. Okay, that's great. I can't see the universe in dark matter in the largest scales, not easily, not with gravitational lensing. So what good is this? So here's the same simulation, except this time they're going to show you where the regular matter is. And so they're zooming in to, that's just showing off, zooming in to one of these kind of nodes in this network. And the blue is where regular matter was, and the green is where the dark matter is. So what this tells you is that if you're simulating your universe correctly, with dark matter and baryons, all you need to do, well, not all you need to do, but one of the things you can do is look for where the galaxies are on these enormous scales. And that should give you a hint about where the dark matter should be. And more specifically, you can compare what they're simulating to what we're seeing. And so what we're looking at here is this is a simulation on this side. So this is kind of projecting now onto the night sky, right? The map of galaxies you should see, this is from the Millennium simulation, and you see that that lattice kind of becomes this spiderweb pattern on the sky. And on the other side is actual observations, right? So this is going out and doing surveys of galaxies. And there's sort of interesting structures. There's a structure called the Great Wall, these kind of big, lattice work of galaxies, and it compares really well, just even by eye, with what you get if you simulate a universe with dark matter. If you don't include dark matter, you don't get such a nice comparison between observation and simulation. So, and then you can do other interesting things. If dark matter was moving very fast in the early universe, it was moving relativistically, it would skip out of small objects. Like there wouldn't be enough gravitational pull to keep the dark matter gravitationally bound. And so if you do what's called cold dark matter, we'd be living in a galaxy in the center here, and there would be all of these sub-galaxies, dwarf galaxies around us. Whereas if you're doing warm dark matter, where dark matter started off moving relativistically, you can see it's all much smoother, right? There's fewer small objects. And this tells you something that's very interesting to me as a particle physicist, which is whatever the hell dark matter is, it wasn't moving at relativistic speeds in the early universe. So I can put nearly everything I know for a fact, every positive piece of information I can tell you about dark matter on this slide. It exists. That's actually, okay, that's good, right? Otherwise, I don't know how to study. It existed in the early universe, okay? That actually constrains things. It's something that doesn't seem to be like popping out of nothing, since the beginning of the universe today. It existed at very early times, it exists today. Okay, some negative statements. It doesn't interact with a strong nuclear force. It doesn't interact with light. That's why we call it dark matter. Things like the bullet cluster tell us that it doesn't interact very much with itself, and it was slow moving when these galaxies were forming. And that's kind of everything I can really tell you about dark matter. So the obvious question is, what is it? And the answer is, we don't know. I do this for a living. This is what I study in my research, and best possible piece of information I can tell you about what the nature of dark matter is beats me. So what could it be? So as I said, I'm a theoretical physicist, or at least that's where I started. Theoretical physicists like nothing more than coming up with really clever ideas to answer problems. And dark matter is a problem. It exists, something that exists in the universe. I hope I convinced you at least of that. So what could it be? What I would say is the leading possibility, whether it will continue to be the leading possibility it's been the leading possibility for 30 years, whether it's the leading possibility for the next 30 years is an open question, is dark matter is something called a thermal relic. So you have to go way, way, way back in time. So I've been talking about nuclei being formed in the early universe. That was when the universe was 1 second old. That's nothing. Go back even earlier, right? So the nuclei were formed when the universe had a temperature where the average photon had an energy of 1 billion electron volts, 1 GeV. So go back to even higher, go back to 100 GeV, and the universe at that point is filled with just things that are moving at insanely high energies. And when that happens, any particle can come along, just smash into another particle. And when that happens, they can produce new stuff on the other side. This happens we do this in particle accelerators. And you just take the kinetic energy of these particles, it would be quarks or leptons or photons or whatever, and you produce something new. Maybe you'll produce more quarks and leptons and photons and particles, I know, but you'll produce anything that can interact with us, with our normal matter, anything that is light enough to have enough energy to produce. And so this is going to go on for when the universe was really hot and really dense, and the universe, as I said, is expanding and cooling. And as that happens, these particles that we know about lose kinetic energy because they're cooling. And it's getting harder and harder to find enough energy in two particles to produce two very massive particles, things that weigh 100 GeV of rest mass. And so it's getting harder and harder to go this way. You're not producing these things very much. But it's an axiom, basically, of particle physics that if you can go one way, if you can produce something, then you can turn everything around and two things can come together and annihilate, go back into photons, let's say. And so whatever this thing is going to be annihilating all the time and producing regular matter. But at the same time that it's getting harder and harder to produce new particles, it's getting harder and harder for one particle to find in this expanding universe another particle to smash into and annihilate. And so this direction shuts off. And so eventually what will happen is that this process will what's called freeze out. It will just stop happening. And you'll end up with these lonely relics, these thermal relics of the very hot universe that will just be floating free in the universe forever. I think basically the idea, so time is going this way, the universe is cooling, this is the number density of these particles, and they're just kind of annihilating away until finally they can no longer find another particle to annihilate, and you get what's called this relic abundance. So this is the abundance of these particles. And the number of these particles you get at the end is related to, well, how hard is it for one of these particles to find another particle? And the way that particle physicists like to think about that problem is we think of it as a cross-section. So my cross-sectional area to you is just literally the surface area that I am presenting to you. If you're looking at my head, it would be a smaller cross-sectional area. So if I was standing here and I had a bunch of ping pong balls and I was throwing them this way, kind of just in a random crowd that way, and you all there were throwing ping pong balls at me, the probability that one of them would hit, one of the ping pong balls going that way would hit a ping pong ball going this way is proportional to its cross-section. Right? Just how big physically is it? So if I throw basketballs that way, it would be a lot easier for them to hit basketballs coming this way. So the bigger the particle, sort of the easier it is for them to find another particle and annihilate. And so it turns out the bigger the particle, the longer this sort of death spiral of annihilation continues, and the fewer particles you get at the end of the day. So if I say, I think this is where dark matter came from, that sounds like a good idea, then I can use the fact that I know how much dark matter exists to say, now I know how big it is. And then if you're a particle physicist, you can take that and turn it into an estimate for how heavy the particle needs to be and what force it interacts with. And it turns out that that force is, the numbers that you get out of it are almost exactly the same as the numbers you get with the weak nuclear force, something I already know exists. That's kind of cool. It didn't have to happen that way. Right? Let's say this is the right answer for the weak nuclear force. The amount of dark matter could be up here, it could have been down here, but it was there. And that's a coincidence. Particle physicists do not like coincidences. So we promoted that coincidence to the state of a miracle. It's called the WIMP miracle, the weakly interacting massive particle miracle. It's not really that miraculous. You do have to work a little bit to get it to actually occur. It's weakly interacting because we say, if this particle is interacts with weak nuclear force, this works. It's massive because it has to be very heavy. And it's a miracle because it didn't need to occur. I do want to point out that for the last 30 years, we've been looking for dark matter as something that interacts through the weak nuclear force. All that I really know, if this is true, is kind of how big it is. So a new force of nature would do the same thing as long as the numbers work out very similarly. And so the nice thing about this idea, though, is that it does say that whatever dark matter is, if this process was how dark matter came to be, then it does annihilate in the early universe with what I've labeled as standard model particles. Right, so dark matter here is chi, looks like X. X is radiating something I don't know, and it's annihilating, I'm claiming, into standard model particles. I want to be clear, I don't know that this is what happened. This is just an idea. It's a good idea, it gives you the right answer, and it kind of has this interesting connection to something else in physics, but it could be wrong. But if you have this and you say, well, this was going on in the early universe, then you can all take your head and kind of turn it in different ways and say, well, today, dark matter would be streaming through this room. If dark matter is a WIMP, one of these particles, then there's about one in a coffee mug going through this room right now. It's going through this room at 300 kilometers per second, so the one in your coffee mug is not staying very long, and another one would be along to replace it. Right? There'd just be a wind of dark matter going through this room. So you could say, dark matter could come along and it has to interact with the standard model, and it could exchange energy and kick this particle off. I wouldn't see the dark matter, but I could see this particle ricochet off. And And I can look for that, and that's something called direct detection. Well, it's very hard for dark matter to find another dark matter particle and annihilate, but it would still happen at very low rates. So you can go and you can say, well, now I'll produce standard model particles wherever there's a lot of dark matter. You will find another dark matter particle occasionally producing new stuff. So you can take your telescopes, or in this case it's a gamma ray telescope that's on a satellite called Fermi, and just start looking in the sky for the relative annihilation of these particles. And so this is called indirect detection. And the last thing you can do is start throwing standard model particles together at very high energies and hope to get dark matter out the other side. So this is collider production of dark matter. And so I'm just going to talk a little bit about each of these options. The idea for direct detection is you have, just take some target, it's got a lot of nuclei in it, you hope that dark matter interacts with your nuclei. That's an assumption, you don't know it's true, but I've given you an argument that says it's not the worst idea in the world. And you look for dark matter to come in and kick this nuclei off with enough energy to be seen. If you work out the numbers, it turns out that any reasonable candidate for dark matter in the story would give you 2 scatterings per kilogram of target material per year. Even if you build the cleanest detector you can imagine and you get rid of every nuclear decaying particle in your detector or near your detector or in the air around your detector, and you bury it 1 mile or 2 miles underground in mines so that you don't have the cosmic radiation that's streaming down on top of you, if you are very, very good, you can get your background down to 1 event per kilogram per day. Right? That's per day, that's per year. Right? That's going to be really, really hard to distinguish this tiny, tiny excess over that. And so you have to work extremely hard to reject any background that can't be dark matter to find your dark matter signal. And they're very good at it. This is one experiment. This is the leading experiment right now. It's called xenon 1 ton. Xenon, because you're using liquid xenon gas. 1 ton for hopefully obvious reasons. The amount of material in it is 1 ton of xenon. And this is down under a mountain in northern Italy. It's not completed yet. I think they're going to be sealing that off at some point. This picture is not completed. It is running now and taking data. I want to point out one really cool thing you can do to try to reduce your background. So if dark matter is really streaming through this room, well, we're going around the sun. That's around the Earth, right? So the sun is moving around the galaxy. So we're moving through this wind of dark matter. And literally it's like running into the wind. You feel more particles hitting your face than your back of your head, very slightly. And so the way it works out is with the solar motion, we move into the wind in June and we move against the wind in December. And that means in June, if dark matter exists and is this kind of particle, it will be hitting our detectors moving ever so slightly faster than it does in December. And that increases your event rate because it has more kinetic energy. And so you can go and you can look for this modulation. And interestingly, there's an experiment called Dama Libra that for basically as long as I've been doing physics has been reporting an annual modulation. Right? This is it. You can see it by eye. Right? You can really easily see it by eye. If you take this line away, you'll be able to pick it out from the data very, very clearly. So that's really interesting. Problem is, it's something that varies over a year. A lot of things vary over the year. Temperature varies. The height of the air column varies. The people who work on an experiment vary over a year. Maybe somebody's a really bad physicist and they go take a ski vacation every December and your experiment changes, right? And here's the problem. As I said, reality ensues. This is an earlier plot. This is the best current limit. This is sort of how much you scatter. This is a mass. This is the best current limit in these units of size, so 10 to the minus 44, 10 to the minus 45 centimeters squared. The signal that I just told you about doesn't appear on this plot. It would be up here. There it is. And we have looked in many, many, many other experiments, and we do not see it, unfortunately. I have no idea what the hell is going on with them. I don't know why they're seeing something varying over a year. They still are, but we just don't know yet. I think the best thing to do would be for them to pack up and move to the southern hemisphere, because then the seasons are reversed and that gets rid of a bunch of but the wind doesn't reverse, right? Because the Earth is still moving into the wind in June. So there are these interesting hints, but we don't really have evidence yet. Now, I know that many of you are here, because you're part of groups that are interested in space and in astronomy, and I just wanted to point out some things. I've been talking as a particle physicist in a bunch of these things, and I'll continue to do that in a little bit. I want to point out that we really need more knowledge, and we really need more knowledge from the astronomers, right? Because everything I just told you was about how much dark matter is moving through this room and how fast it's moving and whether I'm moving into it in one time of the year or not in the other time of the year. And that's all assuming sort of an average galaxy that has this ring of this dark matter halo around it. I don't care about an average galaxy. I care about the Milky Way and where I'm living in the Milky Way. I need to know, are we living in a weird spot? There should be streams of dark matter as things come in from that cosmic web and get ripped apart. It gets literally streams of fast-moving dark matter moving into your galaxy, or there'd be structure. And so what you can do, and what people are starting to do right now, is you can start simulating galaxies. These are all simulated Milky Way type galaxies. And these are just the stars, that you can't see the dark matter in it. But you could, this is a simulation unlike real life. And you can start using that to say, well, on average, an Earth-type planet here, at this point in the galaxy, would see this kind of wind, would have this kind of velocity distribution. What is normal for a galaxy? And what kind of things can I start picking out from what the galaxy looks like to start figuring out what the dark matter looks like? So there's a lot of really interesting stuff here, and I think that's one of, as I'll talk about it at the end, that's one of the really interesting directions for dark matter right now. So for indirect detection, you can, as I said, you're looking for the annihilation of dark matter into something in the universe today. One of the things you can look for is gamma rays. Hopefully the dark matter produces gamma rays and it annihilates. And you need to look for the sort of largest amount of dark matter around, which for us is the galactic center. That's where the most dark matter is, because that's where the most mass is. And unfortunately, the galactic center is a complicated place. There's a black hole there, there's a lot of gas there are stars forming and explosions and supernova and all sorts of crazy things. And you have to look through a lot of dust, and when you look, you see all sorts of amazing structures. There's immense lobes of energetic particles that are emitting gamma rays that stretch out of the Milky Way as high up as we are out. And we only found this actually because we were looking for dark matter in the galactic center. Right? This was a background for that dark matter search, and it turned out to be really interesting and cool because it tells you something about how the galaxy is. What this says probably is that the Milky Way galactic, the black hole at the center, ate something relatively recently, millions of years, and that kicked out a lot of energy in these kind of lobes north and south of the Milky Way plate. But if you work really, really hard, you can subtract off all of those annoying backgrounds that astronomers call really interesting astronomy. And you keep subtracting that off, you keep looking for your signal. And you do that, this is what we call residuals, where you subtract it off everything that you see. You try to estimate what you know should be there from boring real physics, not dark matter physics. Right? And you get this residual, and there's this blob of very high energy gamma rays coming from the galactic center that we can't find any reason should be coming from any known process. That doesn't mean it's not coming from a regular baryonic standard model process, just that we didn't know what was there. It's called the Goodenough Hooperon, or the Hooperon. It's Lisa Goodenough, that is her name. It's a great name for a particle that, it's like, well, that was surprising, but we have a model and it fits, it's good enough. And Dan Hooper, so it's a Goodenough Hooperon, or sometimes just the Hooperon, because he's written the most papers on it. But this is really weird. We need some additional evidence to believe it. So you go out, and the galactic center is the brightest source, but it's really complicated. So again, you go talk to the astronomers, and you say, well, where is there a lot of dark matter, please, that doesn't have a lot of stars? And because the stars are going to screw up my measurements, right? Because they're going to give all sorts of interesting physics that could confuse me as I'm looking for dark matter. And one of the things you can do is you can look for dwarf galaxies. And I don't know if you can see it. This is a dwarf galaxy called Segway 1. And the little circles there are the individual stars in this galaxy. The dwarf galaxy, this is a picture of the Milky Way. Segway 1 is kind of further away. It's kind of off of the disk and up a bit, so it's not close by galactic standards, but on cosmological scales it's nearby. And the nice thing is that I can count all the stars in this object. There's only hundreds, not hundreds of billions. And you can use these stars to kind of estimate using those techniques I talked about how much dark matter there should be there, and you can say, do I see any gamma rays there? And you do that, and this is sort of on cross-section versus mass. This is where you need to live to explain that good enough Uperon, and unfortunately right now the dwarf galaxy limits seem to exclude it. They don't see it. But one thing I'll say is that we need more information. We need more dwarf galaxies. We need to understand their dynamic better. So it's really interesting right now, even if this signal goes away, once you've been doing physics or astronomy long enough, cool signals come and then 5 years later they get killed, and that's really sad, but we keep looking. So even if this signal goes away, if we look at these dwarf galaxies, and if astronomers can build new telescopes and come up with new techniques to tell us where the stars are and therefore where the dark matter is, we can do better and better in these searches. I will try to skip forward. The point here is that you can look for dark matter just by smashing things together at the LHC. This is the two experiments at the LHC, ATLAS and CMS. It's probably the most complicated things humanity has ever built. And you throw protons down the center of it in both directions and smash them together, and you hope that you produce new physics. And they're looking for all sorts of new physics at the LHC. One of the things you can look for is dark matter. That's hard. I can't build a dark matter detector. If I could, I wouldn't be going through this much trouble, right? So what you do is you look for dark matter by looking where it goes, something else has to go the other way. Right? If I'm standing here and all of a sudden I shot that way at 500 miles an hour, you'd be pretty sure that something else had to have gone that way to balance out momentum. So what you do is you smash protons together and you look for something going this way and nothing going that way. Right? So you look for something like this. This is a picture of the detector. There's a huge spout of energy going that way, and there doesn't seem to be anything going that way. The problem is that this is basically the failure mode of the LHC. Anything that goes wrong looks like this. If you miss something, you think you've discovered dark matter. And there are standard model processes like neutrinos that look exactly like this. So it's really difficult, and it's a real testament to the skill of the experimentalists that they can understand these incredibly complicated machines to the level of detail where they are pretty sure that they did not miss anything. They can put a number on how unlikely it is that they missed anything going that way for the trillions and trillions and trillions of collisions they collect. I'll skip that slide. So we're looking, and we've been looking for a long time. We've been looking for longer than I did in physics, and we still haven't found anything. And you can find in the popular press every couple of months another article saying, dark matter is dead. Right? Oh, they didn't find dark matter in this brand new experiment that was going to find dark matter. And so if we continue to not find dark matter in this kind of triad of experiments I've explained, does this mean that dark matter is dead? And I would say no. And the reason is that I have all that evidence I spent the first part of the talk telling you about. Those are observations. They have to have an explanation. Right now, the best explanation is that there is something invisible that has mass that clusters. And that explains every observation that we have made. What we haven't done is found it in a lab, or found it in our detectors, or found it in kind of direct evidence of it coming to us. But this is still a problem. It still needs a solution, and I think that dark matter is the best solution. And I only told you about one possible particle physics version of it. There are many. And again, kind of talking to people who are interested in astronomy and space physics, the only way I know that dark matter even exists for me to try to work on it is because of gravity. Right? Everything I told you about was gravitational probes of the stuff I can see, and I use that to find where dark matter is. So if all of these clever ideas that us particle physicists came up to try to find this thermal relatively early universe scales, continue to use gravity to probe the particle nature of dark matter. And there's a lot of ways you can do that. One thing is that the standard model is crazy complicated. They're not, there's the electron, and then the electron has a muon and a tau. Why the hell are those there? And there are 6 quarks, and there's all these complicated things. And the story of dark matter that I told you right now is that it's just this little thing over there called chi. Well, maybe there is some mysterious, weird, complicated thing that any any particle physicist in their right mind would never have written down because, my God, that's complicated. Why would you do that? But maybe dark matter is only one part of this. And just to say what could happen if dark matter is part of something much more complicated. Well, when you look at a picture in simulations of what a dark matter halo you think looks like, it's a big blob. It's actually much bigger than the galaxy. Galaxies in starlight are these beautiful disks. Why are galaxies disks and these things are blob? Well, it's because the baryons, the protons, can cool. This has a lot of kinetic energy. It's big, it's fluffy, the particles are zipping around. If those particles could emit energy, they would collapse, just like the gas that forms a star would collapse. And then you get these beautiful disks. And so just using the gravitational information I have that tells me dark matter kind of looks like this, it tells me that dark matter doesn't emit something like photons and lose energy. That's actually interesting particle physics information. But that only tells me that down to a certain scale. And it may be that there are collapsed structures of dark matter smaller than the entire galaxy. Again, I'm running late, so I will skip over this a little bit. But I want to point out there are many ways that you can test such ideas about where dark matter is in the universe or in our galaxy. One of the coolest ones right now is a European Space Agency satellite called Gaia. What Gaia is doing is it is looking at the nearest billion stars and measuring how fast they're moving across the sky. Right? Not just how fast they're moving towards us or away from us, which if you know about redshift is relatively easy. They're measuring the parallax. They're measuring how fast a star is moving, that's a kiloparsec away, is moving relative to us. And they can do it down to like 1 to 5 kilometers per second, which is insane resolution. This is the first data release of Gaia. This is the nearest billion stars. And I really recommend go find this on the Gaia website and blow it up. It's incredible. And that's the small version, because if you think of how big a file would need to be to show you the point of a billion stars, they don't want to send out all through the internet for all of you. So this is the low-res version. And you can kind of see there are streaks. You guys see that? Right? That's because the Gaia satellite isn't finished taking data. It's rocking through the sky. Right? Satellites, when they're doing observations, if they're kind of observing the whole sky, they just kind of rotate through the sky and take continual observations as they go. And eventually, they will cover the whole sky evenly. But they did the first data release, and it's not done yet. But you can even find, these are the large and small Magellanic clouds around the Milky Way. So there's an incredible amount of data here. Dark matter is like one of the smallest things that they're going to be answering as for the astronomers. There's so many questions that they can try to address using this data set. And we're really in an era of big data, right, for astronomy. And hopefully you'll hear from, if you've heard, or we'll hear from other professors who are doing more astronomy, not particle physicists moonlighting as astronomers, and they're really looking at these absolutely enormous data sets that were unthinkable decades ago. And all of those things can be used to try to probe the location of where the matter is in the universe, and that means as a particle physicist, you can tell me about dark matter. And I talked about a couple of ideas. This is this direction is easier to find in the lab. This direction is how big of a galaxy I have to look at before I see something weird. I only told you about these models. There's a ridiculous number of models out there in the universe of dark matter that theorists have come up with, and you shouldn't even take this too seriously because that's just saying a theorist came up with an idea, right? So the real answer for dark matter is almost certainly not on this plot, but the thing I want to point out is that what this is saying is if you could tell me about dark matter on the scale of 10 to the 10 solar masses, okay, that tells me about interesting models. If you can tell me about it at 10 to the 6 solar masses or down to the stellar mass or something like that, that can start ruling out for me as a particle physicist what on earth this stuff is. So I appreciate your patience. I went a little bit long. The real takeaway I hope you walk away from this is that there is really good evidence from multiple lines of information that there is a gravitational anomaly out there in the universe, and that the best solution for it is something that I call dark matter, something that is not of the standard model, doesn't interact with light, doesn't interact with strong nuclear force. Beyond that, we don't really know. I described a leading candidate for dark matter. It's been sort of a leading idea for 30 years. It's not the only idea. It may not be the right idea. It's certainly well motivated. It's something we're looking for. We are looking in other ways as well. And I've described those ways that we look for that kind of dark matter. But I think really, I hope that tomorrow I will turn on my computer and read the most recent papers, and there will be a new hint that will turn into evidence for dark matter. And that may happen, right? Because we are looking, and I do think this idea is motivated. But we do need new ideas, and I think really the thing that is an area that needs a lot more work, and will continue to be an interesting area for a long time to come, are these astronomical observations that are being done for other reasons. They didn't build Gaia because the dark matter physicists were asking them to do it. They did it because there are really cool questions to ask about how the galaxy works, right? But if you're interested in dark matter, you can kind of piggyback on all that hard work and hopefully answer interesting questions, and maybe help out the people who are doing other kinds of physics as well, other kinds of astronomy. And I think that's hopefully where things are going. So I'll end there. I'm just going to run the video in the background because it's pretty, and as a theoretical physicist, I don't get pretty pictures. The astronomers and the simulators get really cool pictures that they get to show. I don't. But I just was asked to put this up here. So this is there's a club email list, and this is the QR code, and then if you go to this URL, you can sign up to make sure you can get the emails about future talks.
Yeah, for all three of the clubs, you will, like if you're in one club and you want to join another one of the three clubs that are co-hosting this talk.
So in case you're going to hear that, if you're a member of one of the clubs that's hosting this and want to hear from the other ones, go there. So, and this is just a simulation of a galaxy forming. You're not seeing the dark matter. It is going along in the background, keeping the galaxy together. It's just really cool. And you'll eventually get a nice, beautiful spiral galaxy out of it at the end. Okay, and with that, I'm done. And questions?